Hello and welcome back. Now that we understand the basics of inductors, let's talk a little bit about transformers too. One of the main reasons that we use alternating AC voltages and currents in our homes and workplaces is that AC supplies can be easily generated at a convenient voltage, transformed into a much higher voltages, and then distributed around the country using a national grid of pylons and cables over very long distances. If you were wondering why do we have to transform the voltage coming from the power plant to a higher voltage, which is done by the step-up transformer here, the reason is because higher distribution voltages implies lower currents for the same power and therefore lower power losses along the network grid of cables. These higher AC transmission voltages and currents can then be reduced to a much lower, safer and usable voltage level where it can be used to supply electrical equipment in our homes and workplaces, and all this is possible thanks to the basic voltage transformer. A transformer is a device consisting of two closely coupled coils called primary and secondary. An AC voltage applied to the primary appears across the secondary with a voltage multiplication proportional to the turns ratio of the transformer and with a current multiplication inversely proportional to the turns ratio. Usually transformers are quite efficient. The output power is very nearly equal to input power, and therefore a step-up transformer gives higher voltage at lower current. Now, for a transformer, there is no direct electrical connection between the two coil windings, thereby giving it the name also of an isolation transformer. Generally, the primary winding of a transformer is connected to the input voltage supply and converts or transforms the electrical power into a magnetic field. The job of the secondary winding is to convert this alternating magnetic field into electrical power, producing the required output voltage as shown here. Now let's talk about transformer construction. Notice that the two coil windings are not electrically connected but are only linked magnetically. A single phase transformer can operate to either increase or decrease the voltage applied to the primary winding. When a transformer is used to increase the voltage on its secondary winding with respect to the primary, it is called a step-up transformer. When it is used to decrease the voltage on the secondary winding with respect to the primary, it is called a step-down transformer. However, a third condition exists in which a transformer produces the same voltage on its secondary as is applied to its primary winding. In other words, its output is identical with respect to voltage, current, and power transferred. This type of transformer is called an impedance transformer and is mainly used for impedance matching or the isolation of adjoining electrical circuits. Now, you might ask, how can you achieve a higher or a lower voltage on the secondary coil than on the primary coil? Well, the difference in voltage between the primary and the secondary windings is achieved by changing the number of coil turns in the primary winding compared to the number of coil turns on the secondary winding. As you can see in this equation here, the number of turns on the primary over the number of turns on the secondary is equal to the voltage on the primary over the voltage on the secondary. And if we know this, we can simply say that the turn ratio is equal to the voltage ratio, right? And now let's take an example. If a transformer has 1500 turns of wire on its primary coil and 500 turns of wire for its secondary coil, what will be the turn ratio of the transformer? By doing a simple division, we will get that the turn ratio is 3 to 1. And what does this turn ratio mean to you? Well, it only means that this transformer with 3 to 1 ratio will be a step-down transformer. So the voltage on the secondary coil will be 3 times less than the voltage on the primary coil, right? And now let's see how exactly a transformer works. We have seen that the number of coil turns on the secondary winding compared to the primary winding, which is the turns ratio, affects the amount of voltage available from the secondary coil. But if the two windings are electrically isolated from each other, how is this secondary voltage produced? We have said previously that a transformer basically consists of two coils wound around the common soft iron core. When an alternating voltage is applied to the primary coil, current flows through the coil, which in turn sets up a magnetic field around itself called mutual inductance by this current flow according to Faraday's law of electromagnetic induction. The strength of the magnetic field builds up as the current flow rises from 0 to its maximum value. As the magnetic lines of force, which is created by the primary coil, expand outward from the coil, the soft iron core will form a path and it will concentrate the magnetic flux. However, the strength of the magnetic field induced into the soft iron core depends upon the amount of current and the number of turns in the winding. When the current is reduced, the magnetic field strength is reduced as well. When the magnetic lines of flux flow around the core, they pass through the turns of the secondary winding, causing a voltage to be induced into the secondary coil. The amount of voltage induced will be determined by Faraday's law, where N is the number of coil turns. Also, this induced voltage has the same frequency as the primary winding voltage. Then we can see that the same voltage is induced in each coil turn of both windings because the same magnetic flux links the turns of both the windings together. As a result, the total induced voltage in each winding is directly proportional to the number of turns in that winding. However, the peak amplitude of the output voltage available on the secondary winding will be reduced if the magnetic losses of the core are high. If we want the primary coil to produce a stronger magnetic field to overcome the core's magnetic losses, we can either send a larger current through the coil or keep the same current flowing and instead increase the number of coil turns on the secondary winding. So, assuming we have a transformer with a single turn in the primary and only one turn in the secondary, if 1 volt is applied to the one turn of the primary coil, assuming no losses, enough current must flow and enough magnetic flux generated to induce 1 volt in the single turn of the secondary. That is, each winding supports the same number of volts per turn.